the afternoon session of the first day. And our speaker is Roberto Tateo from Torino. And he will give a talk on deforming the ODEIM correspondence. Roberto?
Okay, yes. So I can start. Hello, everybody. And thank you very much for the kind invitation to speak here. It is very important to carry on this subject and to make intersection between this subject, so the TTbar and irrelevant deformation, with other related subjects like ADS, CFT, etc. Okay, so essentially I'm going to talk about generalization of the ODEIM correspondence involving the perturbation, the TTbar perturbation. And first of all, so these are my collaborators on this subject or related subject. And first of all, I would like to remind you what is the what is about the ODEIM correspondence. So, okay, so this is a rough scheme of the history of this connection as far as I know. Okay, so this the ODEIM correspondence came around, so it's the end of 1998, and I think it's clear that the first paper was by me and together with Patrick, and it is actually an observation. So it's an observation which has many implications. So on the left side of this scheme, there were, let's say, a community working on Schrödinger equation with polynomial or very simple anyway potential, and in particular there were two big let's say important result of let's say way of works coming, series of work coming from Shibuya and collaborators, and this is so there is a beautiful book by Shibuya and is dated 1975. Okay, so he's talking about the Schrödinger problem or Sturm-Liouville problem with generic polynomial potential. And there are important proofs there about unicity of a solution characterized by the asymptotics. In this book and in the work by Shibuya, there was also the emergence of a functional relation that we could call now T systems or a TQ system. Okay. Then some of the result was taken over by Andrei Voros, and this was later than, of course, than Shibuya, about 10 years later. And of course, we know now that, and it gave, so Andrei gave big contribution also to the field. On the other side, there was the development of Bethe Ansatz and integrable model like lattice model, the 6-vertex model, and the 8-vertex model with the works by Baxter. And you can immediately tell that the development by Baxter came in the same period of Shibuya development on the ODE side. So of course, so Baxter and other people introduced the TQ system, the TQ operator, etc., in the context of lattice model. The real connection between with the work by Shibuya and Voros actually comes. Well, it's essentially the Shibuya and Voros work are more related to more recent important development by the group Bajanov, Yulkanov, Zamolodchikov, essentially which correspond to 1994, but of course, TBA equation, Y system, TQ relation were discovered before 1994. Okay, so there were these two lines of research completely disconnected, and there was no hint, apart maybe, probably from random and isolated observation that there was a connection between the two. So our paper in 1998 was about this connection. And why this is important? It is important because tools independently developed in the two parts of the correspondence were flowing from one side to the other and vice versa. So, for example, in the field of integral model, we could use WKB approximation, WKB exact expansion, and on the other side, we could use, so on the ODE side, we could use, we started to use thermodynamic Bethe Ansatz equation, nonlinear integral equation, which were developed much before Voros' work. Okay, so for a few years, for more than, for about 10 years, we thought about generalizing this correspondence to other higher rank, so higher order differential equations, so higher rank integrable system, and also to massive theory. Okay, I think I probably was the only optimistic person on this because we knew that there were special cases where this correspondence was valid also for massive theory and lattice theory. Unfortunately, this generalization were related to particular point with special property. This is, for example, for the lattice model, this is the famous delta equal -1/2 point. Okay, so there was a huge amount of work done between this date here and 2008, where essentially this generalization, so the generalization of critical ODEIM correspondence, so the generalization to massive theory arriving from a different setup, which is related more to gauge theory. Okay, and then there was this very nice paper by Lukyanov and Zamolodchikov. And here also, I think the situation is not clear because there were information flowing between the two groups. And as far as I know, Lukyanov has already some result about the massive case at the same time as Gayotto-Murnay's paper come out. Okay, so we call this massive or of critical ODEIM correspondence because it really there are, the method essentially to treat and to find Bethe Ansatz equation are essentially identical. So the setup it's particularly interesting because this case looks like a way of quantizing a system. So it established a link between a classical theory, a classical integrable theory, and a quantum field theory. Okay, so the starting point here is an integrable nonlinear wave equation like the Sanch-Gordon model or the modified Sanch-Gordon model, but you can generalize it to a fine Toda field theory. And to this family of integrable model, you can find, for this family of integral model, you can find the Lax pair, the Lax operator, and the associated linear problem. Okay, the associated linear problem, as I will show later, is taking the place of the original ODE, so the Schrödinger equation in the first instance of this of the ODEIM correspondence. Then using the same tool, which is a functional approach more related to the Shibuya work, one could get the TQ system for the massive theory, and then Bethe Ansatz equation, thermodynamic Bethe Ansatz equation, Y system, T system, describe the model using local and non-local integral of motion, etc. Okay, so most of the talk I will review this part of the correspondence, so the massive case, and then just at the end I will try to include the TTbar and show you that this classical quantum link or relationship is valid also after you include the TTbar perturbation. Okay, so as usual, I start from an alternative expression for, well, this is called the nonlinear integral equation, sometimes denoted as De Vega equation, but it's actually, it was again discovered before by the Klumper, Pierce, and collaborator group. Okay, so this is an alternative equation to TBA for the Sine-Gordon model, because the TBA for the Sine-Gordon model is changed drastically as you move the coupling constant. So you first have to fix the coupling constant that usually denoted with beta in the Sine-Gordon model, and then you have to derive the TBA equation. So it's not very useful to have a TBA equation which is a family of TBA equation with changing as the coupling parameter is varies. So this is a more compact expression, and of course the two expressions are equivalent and give the same result for the finite side spectrum. So we are in here we are considering the quantum part, so the IM part or IM size of the ODEIM, and this is the De Vega or in general nonlinear integral equation. And we are talking about finite size correction, so energy level at infinite volume. And this is the equation. This is usually called counting function, or I epsilon is called counting function, doesn't really matter. This is called driving term, or we call it driving term because it's the dominant term where when at fixed mass m, when the radius of the circumference of the cylinder goes to become very, very large. Then this is a constant term here, which is usually identified with twist parameter or vacuum parameter. And there is this convolution. So the counting function appear here and here. So this is a nonlinear integral equation, and to find the counting function epsilon, you have really to apply numerical techniques. But you can find epsilon with very, very high precision, up to, let's say, 20 or even more digits. Okay, so you immediately notice here that there is a singularity here when the argument of the log becomes 0. Okay, so this happens when epsilon it's odd, it's pi time an odd integer, and when you fix epsilon to this value, you get exactly a quantization condition. So this the exact quantization condition is implicit. It's contained in the use of thermodynamic type equation like this one. Okay, so when you assume the validity of the ODEIM correspondence, and then immediately you find the exact quantization condition, functional relation, and all you want. Okay, the kernel here is related to the logarithmic derivative of the soliton S matrix, and in here I introduce this S parameter, the scaling parameter, which will be useful for later consideration in the ODEIM setup. And this equation is written in this way is valid only for alpha, which is related to the beta parameter in the Sine-Gordon model greater than 1. You have to change it, modifying just by splitting this integral over two contours above and below the real axis if you go below this value of alpha, if you want to do excited states. Okay, now this Canting function is actually contain the Baxter Q function. Okay, so the Baxter Q function so it's a solution of this functional relation where this it's the eigenvalue, this T is the eigenvalue of the transfer matrix. So roughly speaking, this is the TQ relation, or simply sometimes called just simply a Baxter relation. Okay, so once you know epsilon, the Canting function, you can actually determine the asymptotics of the Q function, of the Baxter Q function. Here we are in the continuum limit, so we are talking about the work by Lukyanov, Zamolodchikov, and Bajanov. Okay, so this is the asymptote. These are the asymptotic of the Q functions, and of course there is a contribution coming from the deriving term, and a contribution coming from this kappa parameter. Then there is another constant contribution here, which, and then you have an infinite series containing the local integral of motion, which we call J, and the non-local integral of motion, which appear when alpha is not an integer. Okay, so this is also, so the introduction of non-local integral of motion is also something new with respect to Shibuya and Voros, because they were considering only polynomial potential and integer power of x to the alpha. Okay, so essentially they were only considered alpha integer. And this parameter here, we will see, is related to the introduction in the Sturm-Liouville problem or equation of regular singularity at x equals 0. So essentially, it's related to an angular momentum type term in the Schrödinger equation. Okay, so this are, as I said, the local and non-local integral of motion, and once you know the Canting function, you can calculate them by doing some integral. Again, for the ground state, the integral runs over the real axis. Okay, and these are the main objects we need at the moment. We are not considering the non-local integral of motion, which have also an important meaning in the on the ODE side of the correspondence. So, for example, if we consider a J1, a J bar 1 defined in this way, you can reconstruct the energy at finite R of the state. We will mostly concentrate on the ground state energy because most of what we know about the ODEIM, at least for the massive case, is involved in the ground state. Okay, so the energy is can be written in this way in terms of the J1 and J bar 1, the local charges. There is this extra term here, which is related to the driving term. We usually call it a bar term. And this is the momentum, which in this case is obviously 0. So J1 is equal to J1 bar, okay? And the coefficient here can be identified for alpha greater than 0 with the mass of the fundamental breather. Okay, now we know how to include the TTbar deformation inside this setup, inside this nonlinear integral equation setup, and we know that we have to modify the S matrix So the soliton S matrix, which gives you the kernel of this nonlinear integral equation by a CDD factor, and this which depend on the parameter tau here. So this CDD factor, it's very simple. It's the exponential of I tau with this coefficient here, sine hyperbolic of theta. If you put it in the equation, then you have to replace the kernel in this simple way. Okay. So this modification of the kernel can be actually formally reabsorbed in a redefinition of the driving term. And this is the redefinition. Mr sine of theta goes to M, something which I call R0, which depend on tau, and sine of theta minus theta 0, where theta 0 also depend on tau and the energy level under consideration. Now, R0 and theta 0 can be obtained using this pair of relation, which, as I said, would fix theta 0 and R0. Notice also that if P equals 0, as for the ground state, theta 0 is 0, and so you only need this equation, which becomes R0 is equal R plus tau E, the ground state energy. Now if you use this parameterization in the nonlinear integral equation, then it's easy to obtain. It is really straightforward to obtain a flow equation for the spectrum. And this is the famous Burger type equation for the spectrum. So it means that if you know the spectrum at tau equals 0, then you solving this equation, you can also find the TTbar deform spectrum of the theory. So this is an hydrodynamic type equation, which is well known in the literature, and in hydrodynamic.
Roberto,
yes.
Sorry, Roberto, I think there was a question from the audience, right?
Yeah, Roberto, may I have a question?
Yes.
Yeah, so you said that this kernel is coming from soliton S matrix, and that's why you add this tau dependent terms. But another original derivation of this nonlinear integral equation is actually can come from lattice construction, something
yes.
like this vortex model. And
yes.
the kernel can be related to Boltzmann weights of this 6 vortex model.
Yes, yes.
So,
yeah.
So do you have this lattice meaning of this tau TTbar information tau dependent form?
Yeah, I didn't work on that. Maybe you should wait for the, make the same question to Yunfeng. I think he knows more about this, but there are certain attempts to generalize this TTbar deformation to lattice model. Okay, so I don't want to fully answer your question because I might say something which is actually not correct or wrong. Okay, so as I said, using this step, just working inside quantum field theory on finite size geometry, you can find this Burger equation, and we all know that this wave breaking phenomena here in hydrodynamic correspond on this setup instead of the appearance of branch point or Hagedorn time singularity, for example, for the ground state energy for a particular sign of tau. Okay, so now we can move to the ODE side, and the ODE side is involving, as I mentioned, an integrable classical model. And in this case, also in the case I want to discuss, it is involving the Sanch-Gordon model. So it's essentially formally an analytic continuation of to imaginary coupling of the Sanch-Gordon model. Okay, so in this respect, as I said, the ODEIM for this model with this modification correspond to a quantum classical duality. Okay, so this is the modified Sanch-Gordon model. So it's modified because you have introduced here this function P of Z times P of Z bar, where P of Z has this simple form. And we will see that this P of Z is actually, will take the, correspond essentially in this ODE side to the Schrödinger potential, the anharmonic Schrödinger potential. Okay, so there is no much difference between the modified Sanch-Gordon equation and the unmodified one, because you can change variable, so move from the Z and Z bar variable or coordinate to the W and W bar coordinate, and make a redefinition of the field eta in this way, and you can easily map this modified Sanch-Gordon equation to the unmodified Sanch-Gordon equation. So we are really talking about Sanch-Gordon equation, maybe with particularly boundary condition. Okay. So next step, as I anticipated, is the introduction of the Lax pair. So this is the Lax pair for the modified Sanch-Gordon model. So I call it as D and D bar. I'm actually taking material from the Lukyanov-Zamolodchikov paper. So you can go there and reconstruct everything I'm saying here. Okay, so these are the Lax operators. So P appears here and here, and the sigma are Pauli, the sigma 3, sigma plus and minus are the Pauli matrices. So associated to this two pair of operators, you have the associated linear system, which correspond to these two this two pair of equation, d psi equals 0 and d bar psi equals 0, with the same psi here, and the Sanch-Gordon, Sanch-Gordon equation of motion comes from the consistency between these two equations. So I multiply this by d bar and this by d and take the difference, and the result should be 0. Okay, so another way to rewrite this system of first order, because this is first order derivative differential equation, is to change parametrization for psi. So parameterize this the psi here, which is a 2 vector, in terms of this psi here, small psi here, and this psi bar there. Okay, so if you do this replacement, actually this system, we can reduce this pair of Lax equation into this system here. And now you can really see why there is a deep relation with an ODE. So if, for example, if you consider this equation here, Z bar, you can consider it as a parameter, and this is nothing else than a Sturm-Liouville type equation, so a Schrödinger type equation. Okay, and so, but they are coupled in this way, because here in the U part, which is defined in terms of the solution of the Sanch-Gordon, of the modified Sanch-Gordon equation, it appears both Z and Z bar. Okay. Now, how do you get the standard or the old ODEIM? So for the conformal field theory, you look for a particular solution which has this asymptotics. So eta goes like n log of z bar plus n0, and you are concentrate on the leading asymptotics by sending z bar, so one of the coordinate z and z bar that you might consider as independent coordinate to 0. Okay, so in this case, the field solution is dominated by this term here, and you can do a rescaling of the variable. So you send z and s to 0 such that x defined in this way remain finite and e defined in this way remain finite. And then what you get at the end is this Schrödinger equation. So this is the family of Schrödinger type equations studied by Voros, Shibuya, etc. Apart maybe that Shibuya mostly studied the more general case with polynomial potential. So this term here is new. As I say, this was introduced by Bajanov, Lukyanov, Zamologikov. Okay, this regular singularity at x equals 0. Okay, but yeah, so apart the initial input about the nonlinear classical equation, then once you arrive to this point, essentially the treatment is the same as before and essentially match what the Shibuya analysis for polynomial potential. Okay. Okay, so we are on the classical side. As I said, the ODEIM, it's a match between the quantity, classical quantity and quantum quantity. On the classical side, so on this the side we are discussing here, this local integral motion are defined as usual in terms of the currents, of the conserved currents, with an integral. Okay, I specify more what this contour of integration is later. Okay, the simplest case concern, as I say, the most interesting case concern n equal 1, and this put a relation, this establish a relationship between the T mu nu, the component of the stress energy tensor in a complex coordinate, and the field U and U bar, and the explanation of the field defined somewhere here. Okay. And at this stage, so eta hat, the solution of the Sanch-Gordon equation and not the modified Sanch-Gordon equation is involved for simplicity. Okay, so this means that you can reconstruct the energy and the momentum. As I said, for the ground state, the momentum is 0 in this way. So, and so the main claim about the ODEIM correspondence is the following. Okay, so is the following, that the set of local conserved charges is equal on the two sides. So the quantum definition gives the same answer as the classical definition. Okay. Okay, this is valid, as I said. So this is, you know, there is no tau involved. There is still no TTbar perturbation. So this is the claim for the of the ODEIM correspondence at tau equals 0. So a full match between local and eventually non-local integral of motion on the two sides of the correspondence. Okay, so you might notice that there is some missing point. So in here, I wrote only also on the classical side that there is an R dependence, so that we are at finite volume. So first of all, we need to understand what R mean, or what's the object associated to the circumference of the cylinder on the classical side. Okay, and essentially this is a WKB integral. So R is defined in this way, which actually the definition is more transparent if you map the W variable into the Z and Z bar variable. So this is the integration contour, is gamma 2 and gamma 2 bar, which is the reflected contour. And it's really starting, this is the contour just above and below the real axis, and this is the inversion point of the potential, so which correspond to Z equal S. Okay, so it's running from the inversion point and going to infinity above and below the real axis. Okay, this is a standard object we used to calculate when we were, you know, trying to find, for example, the leading asymptotic of the WKB approximation for the wave function. Okay, so next step is to introduce the TTbar deformation at the classical level. Okay, at the classical level, we are not talking, no longer talking about CDD factor. We are talking about a change, a dynamical change of coordinate. So a change of coordinate which depends on the field configuration and is actually involving the component of the stress energy tensor. Okay, so this change of variable, which for example is mapping the perturbed equation of motion into the unperturbed one and vice versa, it's characterized by a Jacobian transformation, which is involving a perturbing parameter T, which one can see that is actually related to the tau parameter I introduced before by this relation, and it's just a different normalization due to a different normalization we have used for the definition of theta 0 and T, so the component of the stress energy tensor. Okay, so this is the Jacobian transformation, which is, as I said, mapping the unperturbed equation of motion in the TTbar perturbed equation of motion and vice versa. Okay, so now what we need to do is to try to understand how this circumference R, okay, so defined in this way, is modified through the introduction of this TTbar perturbation, so through this map associated with this Jacobian transformation. So we start from this expression here, and we do the map. So we change variable, we move from the W variable to the X and X bar variable. And the result is the following, that this integral becomes split in two parts. So one is the integral over gamma 1 on the X plus a term which is proportional to the perturbing parameter T. Okay, so this contribution here is actually exactly the energy of the state, and therefore at classical level we obtain this result that R is modified becoming R tilde plus, so and R tilde is equal to R plus tau, the energy of the state. In this case is the ground state energy. Okay, so we see that the change of R is actually identical at classical and quantum level. So this might already be essentially interpreted as the proof of the validity of the ODEIM also with TTbar, but let's try to calculate, to be more precise. I think we need to calculate the flow, to derive the flow equation on the classical side. Okay, so we would like to show that using this result, okay, we can prove that we have a flow equation for the energy. So we would like to prove the validity of this Burger equation on the classical side. Okay, to do that, we start from this expression here, and we keep fix R tilde. So it means that you have a relation between R and T. So R is moving as you vary T. So we fix R tilde and we take the derivative with respect of tau of the previous equation, and this is what you get. So there are explicit dependence on tau, and there are implicit dependence on tau inside the energy level under consideration. So this is what you get, and you see immediately that to find to obtain the Burger equation, you have to prove that this term here plus this term here goes to 0, and which means this, and automatically if you plug this result in this, then you see that the energies fulfill the Burger equation. Okay, so to prove this relation, we just have to do the same calculation, but infinitesimal. Okay, so essentially now we fix, so this was the definition of R tilde. So in this definition, you see this contour of integration is depending on the parameter tau or the parameter t. So it means that R tilde is completely related or directly related to this integration contour gamma of t. Now we want to fix gamma t, and so it means that we have to find how gamma 1, the original contour, is changing as we vary t. So essentially, before we were keeping fixed gamma 1 and see how, and changing gamma t or gamma tau. Now we do the vice versa, but of course the calculation is essentially the same, keeping gamma tau fixed and see how gamma 1 is varied. Okay, so to do that, we introduce some other variable with a different name. So we call RT this quantity, and R of t minus delta t this quantity here. And now we just want to find the transformation between the x coordinate and the y coordinate. So this is again a Jacobian transformation that it's contained in the Jacobian transformation defined before, and this is the change of variable between the x coordinate and the y coordinate. So this is the change of variable. So you do the calculation, it's essentially identical to what we did before, but in this case you find the infinitesimal variation of R, which involves the infinitesimal variation of the parameter t. Okay, so out of this, you essentially get immediately the relation we want. Okay, so this means that what we had is that we proved the flow equation, the Burger equation for the flow, both at classical and quantum level. So, and essentially this is enough to prove that the ODEIM can be extended when you perturb the theory with TTbar. because of course this is a first order differential equation in tau. So if at tau equals 0, the two theories are the same, then when you switch on the tau parameter, they evolve with using through the same Berger equation, and then the result is the same also at tau different from 0. So this is, let's say, the small result I had, I wanted to present, so that you can extend this ODEIM correspondence in the presence of a TTbar perturbation. And the TTbar perturbation corresponds to acidity factor at quantum level and to a change of variable, a dynamical change of variable at classical level on the two sides of the correspondence. So I can conclude. So this is what we prove. So validity of the ODEIM correspondence in presence of the TTbar perturbation. And what I can say is that we are at the beginning, so we don't fully understand the whole implication of this extension. But what we know is that, of course, you can generalize this proof to a generic polynomial potential. So your generic P of Z or P of Z bar, you can generalize it to a higher order system like a Toda field theory, etc. So with multi-field system, and of course the outcome is the same because the Berger equation is the same for any field theory perturbed by TTbar. And of course, one of the things I would like to understand is how this modification of this classical quantum correspondence affect the result on amplitude and Wilson loop in the ADS-CFT framework. Okay, I think I have done. Is there any question?
And thank you, Roberto. Let's speaker first.
Hi, Roberto. I have a question.
Yes.
So, here you show that TTbar deformation basically preserves ODEIM, and then you also have defined a more general deformation, which also affects the length of the system, but by higher charges. I guess,
yes.
Does those perturbations also preserve ODEIM?
Okay, so let's say in the family of deformation, what we usually associate to Smirnov's homological work, there are a subset of deformation which still correspond to a change of a dynamical change of variable. And I think in that case, it is obvious that this can be extended. But there are also other cases, usually spin zero, what they are called TTbar N or something like that, spin zero deformation. And in that case, those deformations are not, as far as I understand, are not associated to the dynamical change of variable. And so that case, I think, should be studied apart, I mean, in an independent manner. So I think in that case, I don't even know what's the lax, how to obtain the perturb lax operator. Maybe you know, maybe you are working on similar stuff, but I think you are working on everything essentially. But I think the main problem is that I don't know the form lax operator, so I cannot make any big claim. But I suspect, yes, I mean.
Thanks. So another question is, I mean, it's great to establish that TTbar preserves ODEIM, But does this teach us something new about TTbar? What can we learn? I just understand about.
Well, no, I think, I mean, yeah, you know, once you know that the TTbar classical level is correspond to a change of variable, it was almost, you know, I don't say obvious because you have to prove it, but the feeling it was that it, you know, this ODEIM could be extended with TTbar. But I think this is the proof, and you know, in the back of your mind, you always think that there might be some subtle point which make things not working with TTbar. But I think at this stage, at least for my point of view, is not adding more about you know, no extra tool or things like that compared to what we know about you know, ODEIM and TTbar, etc. Okay. Okay. The hope is that really maybe, I mean, you can include this. You know, use ODEIM in string theory and understand more about TTbar perturbation in ADS-CFT. So even the work by Lever-Linder and collaborators on TTbar. Okay, but I cannot tell much. I mean, I don't know much essentially.
Okay, thank you very much.
Okay,
you're welcome.
So this morning we heard a very nice talk from Prairie about this singularity developed in the iteration procedure of solving TBA equations. And I'm sure that this nonlinear integral equation also will have the same kind of singularity problem.
Okay, so I think
any this ODEIM correspondence can say anything about this kind of singularity in this differential equation point of view?
Yeah, I don't know. I wasn't, yeah, in your morning time, I wasn't there. So, so this is a talk of this morning.
Right. So then, yeah, so he said that using not this iteration of the using driving term as a starting point, if you iterate this equation using this driving term as an initial condition, then you meet certain singularity at certain value bar. But if you propose some other kind of iteration, but that's not the point. My point is that since this TBA or NLI will have such a kind of instability at certain value of the R, and there's some issue on how to interpret this kind of singularity. But what is a corresponding statement in this ordinary differential equation?
Yeah, well, I'm answering blindly. I think that often, I mean, this WKB type tool or exactly WKB type tools coming from the ODE side, I think they're useful. I mean, they're useful to extract concrete information that are more difficult to extract from TBA or nonlinear integral equation. I mean, in some case. So
you are saying,
I think,
please.
I just wanted to add to Professor An's question. So actually, I think he's referring to this TTbar deformation of this recent work by Zamolodchikov, where they take a different set of TDD factors.
Okay.
These are the ones which you mentioned doesn't have a dynamical change of coordinate interpretation. And for those guys, there are also singularities in the spectrum, but you have to solve TBA to see that. So the question, I think, is that can you see this kind of singularities more easily from the IM side without going through this numerical pain?
Okay, I understand now the question. I think the problem goes back to your first question, is that we don't know the extension of TTN, the spin zero TTN of the ODEIM correspondence. So I think that's, but then probably at a certain point, if you find that, probably I think this ODEIM can help in that. Because you can apply semi-classical method, standard WKB method for the spectrum, and sometime, I mean, you can really extract very easily important information. So,
any other questions? Okay, so if there is no additional questions, let's thank Roberto again.
Thank you very much. Thank you. Thank you for your attention.